Hi everyone, my name is Rob from RobOps, and today I'm going to show you how to build your first machine learning model from scratch. If machine learning feels abstract or intimidating, this is the kind of project that makes it real. We're going to take a real data set, define a prediction problem, build a baseline, train a model, compare results, and then test a more advanced approach to see if it actually helps. By the end of this video, you should understand the practical workflow for building your first machine learning model, and more importantly, how to think about whether the model is actually useful. At a practical level, machine learning is the process of using historical data to learn a pattern that can help us make a prediction. In this video, we're going to be using past housing market data to predict future housing benchmark value. The repository for this video uses a Toronto housing dataset stored as a CSV file from Kaggle. This is not a dataset of individual home sales. It's an aggregated monthly market dataset with location level benchmarking values and related housing indicators. On the technical side, the project uses Python with two core libraries that are very typical for ML projects. We use pandas for loading, inspecting, cleaning, and reshaping the dataset. And we use scikit-learn for the machine learning workflow itself, including pre-processing, training, and test splitting, model pipelines, metrics, and the regression algorithms we're going to be using to actually make our predictions. Instead of predicting the price of an exact home, what we're going to do is predicting the next month's benchmark price. So you can think of it as like an aggregate price for a given location. That means our project question is, given the current month's data for a location, can we predict the next month's benchmark price better than a simple baseline? This is a very realistic first machine learning project. If you are interested in the code itself, everything will be available on my GitHub page, linked in the description. There are really 5 core steps here. First, we define the problem clearly. Second, we inspect and clean the data so that it's ready to be modeled. Third, we'll build a baseline so we know what good will actually look like from the results of our model. Fourth, we'll train a very simple model with training and test data. And fifth, iterate and improve if the change actually beats your current best version. That loop is the core of practical machine learning. So if I scroll up here and go into my data set, I'll notice I have a CSV file here. And if I open that up, I'll notice I have about 5,000 rows of data here. And so the first thing we want to do is load that CSV into a pandas data frame. That gave us a table we could inspect with things like shape, column names, data types, missing values, and data coverage. All of the things we need to actually analyze and clean our data set. When we inspected it, we found that it had just over 5,000 rows and 17 columns, including fields like location, compensation benchmark, comp index, comp year-over-year change, and date. We also found missing values in some of the property type columns, especially townhouse and apartment related fields. This is very common with public data sets. They're very rarely perfect, and so some cleaning is almost always required. This is the important part, because the easiest way to make your first model harder than it needs to be is to pull in messy features too early. So for version 1, we kept the feature set intentionally small. And so here I'm in my terminal, and I am going to simply just inspect this data set, and it's going to do some various analyses that you can see in this inspect dataset Python file. But effectively, I'm going to run it. And as you can see, we can see the power of what pandas can do for us. And so we basically are able to get the shape, which is 5,000 rows and 17 columns. Those columns are made up of the following indexes. And then we can actually sample some of that data so you can see some of the locations and get a feel for the actual data, along with the data types. So you can see a very typical thing that we'll do is like this date, we'll convert it to date time. Because we are doing a time series analysis, we do need the date value to be the right type. And then as you can see here also, we see some of these values, and we can see also some of this missing data. And so you can see the townhouse and apartment data has higher missing percentage than a variety of the other things. And so for the analysis, like we mentioned earlier, we would probably exclude these things. The key step in this project was turning raw historical data into a supervised learning problem. Each row in the raw data set represents one location in 1 month. But we don't want to predict the current month. We want to predict the next month. And so in pandas, we did that by grouping the data by location and shifting the comp benchmark column forward by 1 row. That creates a new target column representing next month's benchmark. Functionally, each training row now means here is what we know in month X, and here is the answer in month X plus 1. That will allow us to accurately train our model because we'll now have direct results in the same row. And so when we come over the code, we can look at this load dataset function, and what we'll see is effectively using pandas to read the dataset that we have and do some conversions to ensure that we have the date in the right type and sort by location and date. The other important piece is the building the model. And so here is what we're going to actually bring that comp benchmark from the previous month forward. And so here you can see that we're grouping by location and comp benchmark, but we're shifting it forward by 1. And so effectively what that's going to do is it's going to augment our data set, and it's going to add the future month to each of the rows below it. Before training any model, we have to establish a baseline. A baseline is just a simple rule that gives us something to compare our results against. For this project, the baseline was predict that next month's benchmark price will be equal to the current month's benchmark price. Meaning our prediction is that the benchmark price doesn't change at all. Now that may sound simple, but it's actually a strong baseline for things like time-based data. If your machine learning model cannot beat that rule, then the model is probably not adding value. That's one of the most important concepts of machine learning. A model is not useful just because it runs. It needs to outperform a reasonable alternative. And so the actual results we're going to compare to are nothing changed. And so if the benchmark changes and the delta is greater in our prediction than it is to our benchmark, which is nothing changes, then our machine learning model isn't actually doing very well. Now, if we come back to the code and we want to see where that manifests, we can just see it in the run experiment function. And you can see we have like this baseline. And effectively we evaluate our predictions against our testing data against our baseline prediction. And that's going to give us our baseline metrics, which are the MAE and the RMSE. Another important concept here is we actually have to split our data to train our model. And the way that the training works is we have historical data that is used as the training data. And then we have testing data, which we test our predictions against to calibrate the model itself. And because we're using a time series or a time-aware training data set, doing the split needs to happen chronologically, and this is important. And so because this is a forecasting problem, we cannot randomly split the data. That would leak future patterns into the training. So instead, we trained on earlier data and tested on later dates. So in this repo, the training data runs through to the end of 2019, and then the test data starts at 2020 onward. The split is implemented directly in pandas by creating a date-based mask instead of randomly splitting the data out. And so this is a technical detail worth noting because many beginners may reach for random training and test splitting by default. But if it's a forecasting problem, meaning a time series data set, it needs to make sure that we are splitting the data correctly. And so tactically, we have a split training test data here, and this will show you how we create this data frame, and the actual masks itself are based on dates that are above or below this split date. And so this is a good way to use pandas again to help us analyze the actual data and prep it for the actual training of our data. So for the first model, we used linear regression from your basic statistics class from the scikit-learn library. The features we used were location, year, month, comp benchmark, comp index, and comp year-over-year change. Because location is text, we had to do a little bit of handling to allow it to be processed. And so the scikit-learn kit has a feature called one hot encoder. Effectively, all you need to know is it's taking the text and converting it into a numerical representation. And then we use a column transformer to apply the encoding so that the location is able to be processed by the model. And then we wrapped the pre-processing and the model together in a pipeline. And this pipeline is what's actually going to train our data set. And this matters because it keeps the pre-processing and the model as one repeatable workflow instead of a bunch of separate manual steps that we're running one after each other to train the data set. And so here you can see we're using the import linear regression. And if I go down to the actual pipeline itself, we can see that the preprocessor is being defined here, and we pass that in as a step in the pipeline itself. And this pipeline is what's going to actually run our experiment. Now let's run the best version of the model. This experiment uses the core features only and compares linear regression against our baseline that we had established earlier. To measure, we use two evaluation metrics from the scikit-learn kit. MAE, which stands for mean absolute error. This tells us the average size of our miss. And RMSE, which stands for root mean squared error and penalizes larger misses more heavily. So in order to do this, we're just going to pop open our terminal here, and I'm just going to run model .py, and then the experiment is linear core, which is the linear regression here. And so this model is going to run, and we're going to get our results. Because the data set is not very large, it doesn't take very long to run. But what does it tell us? An MAE of about 17,3828 and an RMSE about 22,853. And the linear regression model gave us an MAE of 15,456 and RMSE 2055. So what does this mean? It does mean that the model improved on our baseline by about 10%. This is actually a very meaningful result. It does not mean that the model is production ready, of course. It means that the workflow is valid. The feature carries a signal that our predictions will be on average 10% more accurate than if we had just assumed that the comp benchmark would stay the same month over month. This is exactly the type of improvement we would look for our first ML project. So if you remember from earlier, the next step here is how do we improve on that 10%? So we tried to do that by adding a lag feature. And basically lag features are just adding more data points to our training row, like the previous month or the previous month's benchmark 3 months ago. What was the comp benchmark 3 months ago, and a rolling average of prior months. We created those with pandas as well, using group bys and shifts and rolling, which are all features as part of the pandas library that helps us kind of shape some of these training data rows. Conceptually, it makes sense. If we have more data points, we should be able to infer better future results. But when we retrained it with linear regression, those lag features made the model slightly worse. So this is another important part of machine learning. More features do not automatically mean better results. So then we tried a different algorithm. Of course, linear regression is one algorithm. We tried something called the random forest regressor from the scikit-learn kit, using the same lag-based data set. And that model performed even worse than the baseline and the simple linear regression model. So again, very useful. A more complex algorithm is not always a better algorithm. Sometimes a simpler model generalizes better. If you are interested in seeing those, we did set up the repo in such a way that you could append the experiment type. So linear lag is the additional features that we added. And so you can train the model again, and you'll see compared to the baseline, better than the baseline, but not as good as the results that we saw. And then with the new algorithm, along with the lag features, what we'll see is, again, training takes a bit longer, but in fact, we are worse on the metrics than the baseline with those results. And so I'd invite you to kind of pull the repo, try this, see it for yourself, and you can kind of like get your hands on some of the outcomes that we're seeing here. So the main lesson from this project is not just how to import a model from scikit-learn and call fit. It's how to think through a machine learning problem in a disciplined way. We defined the question clearly, we inspected the data before training, we chose a baseline, we trained a simple model before trying more complicated ones, and we evaluated on unseen future data. And we kept only the version that actually performed best, which was the one we showed first. That is the right way to build machine learning systems. Technically, this project also introduces a lot of core mechanics you'll see again and again. Loading data with pandas, cleaning and filtering rows, engineering features, building a supervised target, and encoding categorical variables. We also used a pipeline, we trained using scikit-learn, and we evaluated with clear metrics. Those are all the foundational skills you will need to build your first ML model. Now, I don't claim to be an expert. I am doing all of this learning on my own, but I did find this very interesting, and I hope with this video to provide structure to how to approach these problems so that we can scale this structure to more complicated problems. Like I was mentioning before, this project is basic by design, but the workflow scales surprisingly far. Larger machine learning systems still depend on the same core ideas: clear target definition, cleaning data, baseline comparison, honest validation, and iterative improvement. Even advanced systems, including the kind of models that power modern AI applications, are still built on disciplined experimentation and evaluation. So if you can understand this workflow, you're building the right mental model and foundation. If you want to see a follow-up, the next natural step would be things like visualizing predictions, saving the trained model, trying regularized linear models like Ridge or Lasso, or moving to a more structured experiment framework. If that sounds useful, let me know what you would like to see next, as this is part one of hopefully more parts of our machine learning series. And once again, I want to say thanks for watching. If you did enjoy the content, please consider liking and subscribing. It really helps me out, and I hope you have a great week.